Okay, MEGN 300, welcome back today. We're going to be talking about uncertainty and error analysis. So this is how we will talk about how do we know how good our instrument is and what are the limits to what our instrument can detect. So to do that, we're going to need some background in some statistics and some other mathematical techniques, which we will then apply to the data that we collect when we're calibrating an instrument to determine things like the resolution of the instrument. So that's kind of what we're doing today. All right, so here's where we're trying to head, right? So what we want to be able to do with your scale project is we want you to be able to make a calibration curve and then put error bars on the experimental calibration points so that we know what the uncertainty around every point on your chart is, and then we can compare to a theoretical calibration curve and see if our experiment is within uncertainty of what our models originally predicted. That's what we're going to be trying to do. All right. So to talk about this, first we need to talk about where uncertainty comes from and why this is a thing. So if you were to take an instrument, and in this case our instrument outputs some sort of volts, right? This is just a generic instrument. It doesn't matter what it's measuring. It outputs volts, and we're going to measure the same exact thing multiple times here. So we have a whole bunch of data points. We're looking at the exact same value of our measured variables. There shouldn't be any changes. In a perfect world, all of those dots would be exactly on the same line there, and you'd have the exact same measurements. But that's not what happens. In the real world, we have noise, right? So noise is just random fluctuations of our measured variable due to all sorts of things. Thermal expansion, there's actual electronic effects that happen inside of electronic components that cause things to not work exactly how they're supposed to. And that's what we have. So we get random variations on any real experimental system. That's unavoidable. We can't do anything about that. What we can do is we can quantify the noise, and we can learn to know what the noise is and then work around it as engineers. So what we're going to be talking about is how we do that. So if we were to take this data set here and we were to look at that, it's forming a Gaussian or a normal distribution around a mean value, right? And if we don't have any bias errors in our instrument, or if our instrument's well calibrated, then the mean of that data set should fall exactly on the true value of our measured variable, okay? And it's going to have a standard deviation, this data set also. So this standard deviation describes how spread out the data is. So big standard deviation means we have a lot of precision error, so we have a lot of variation from the mean. Whereas a small standard deviation means we have a very tight distribution, we have a very repeatable measurement, a precise measurement. Okay, so that seems all right, and we could just take a bunch of data and then take the mean of it, and we should get close to the true value. But the problem is, to perfectly know what the mean and the standard deviation are, we need an infinite number of measurements. We need to take all the possible measurements that we could with the instrument, but the problem is we could always take another one. So there's an infinite number of possible measurements that we could take with this instrument. So we can't do that practically, right? None of us have time to sit around and take an infinite number of data points. So we need a better technique to take a few data points and get a really good estimate of what the mean and the standard deviation are. So that's the first technique that we're going to be talking about. Now, this technique was developed by an English statistician and chemist named William Seeley Gossett. Right, there's his picture and when he lived. He graduated from Oxford in 1899, and when he graduated, he got hired by this company that at the time was kind of like a Google or Apple, one of these big companies that was really investing in hiring a lot of very bright people and giving them a lot of academic freedom on how to improve their process. They're basically just getting all these smart people together and hoping that they would come up with ideas that would give them a competitive advantage in the marketplace. And a lot of people are surprised to find out that this company was in fact Guinness Brewing from Dublin, right? So yes, the stout beer company was really thought of as a forward-thinking company at the time. And the reason they were doing this is because at the time, Guinness was really scaling up their production and becoming one of the world's first truly industrial scale breweries. So around 1900, Guinness was scaling up to produce about 1 billion pints of Guinness per year. That's billion with a B. That's a lot of beer. This is a picture of the cooperage yard. All right, so the cooperage yard is where they made barrels that they would transport the Guinness in. And you can see they're using draft horses to drag those barrels around, and you can see how small a draft horse is compared to those stacks of barrels. So this is just a tremendous amount of beer that they're producing and selling all over the world. Now, the problem with that is if you want to have a consistent product so that a pint of Guinness always tastes the same no matter what pub you go to or what time of year you go to the pub, you need to account for some of the natural variations that you're going to get in your ingredients when you're making your beer. So beer is made out of malted barley, hops, water, and then yeast added, and particularly the malted barley and the hops are naturally grown agricultural products. They're going to have some variation depending on where they were grown, how they were grown, how much it rained while they were growing. And to make your beer consistent, you need to account for those variations in your brewing process and tweak your brewing process so that the beer comes out exactly the same every single time. Now, it's not possible for them to take all these train cars of barley and hops and all of this and test every batch of ingredient really exhaustively to really nail down what the properties of that ingredient are. So what they needed to do was they needed to have a way where they could take a few samples of their ingredients and come up with a good enough estimate of its properties so that they could keep their brewing process within acceptable limits. All right. So that was the motivation behind this technique that William Seeley Gossett came up with. So his solution that he came up with is actually a probability distribution, which is known as student's T distribution and table, right? So the question is, why isn't it called Gossett's T distribution and table? It was published under a pseudonym Student because when William Seeley Gossett came up with it, he recognized that it was a major contribution to the field of statistics. But Guinness was really wary about having him publish it under his own name because it was such a huge competitive advantage for them. They didn't want any of the other breweries knowing that they were doing this, right? Because this was totally innovative. Nobody else was doing it, and it was a huge deal and really streamlined their process for this industrial scale brewing. So the compromise they came up with is to say, hey, you can publish your work, but you can't put your name on it because then nobody can know that it was one of our employees that came up with this technique. All right. So essentially what this does is it describes a confidence interval, which is a range of values where if you take a whole bunch of measurements and you derive a confidence interval from those measurements, you come up with this range of values where you're likely to find a next measurement, right? And we determine this confidence interval from two values. We call X bar and SX, all right? So X bar is the sample mean and SX is the sample standard deviation. Now, that's different than the variables that we showed previously where we used mu for the mean and sigma for the standard deviation. And that's because those two values are more for the population mean and standard deviation. So if you have the entire possible range of measurements, you can talk about calculating mu and sigma. But for a sample where there's many samples out there that are unknown, right? Many data points that we don't have. We just have a small subset of those data points. There's the sample of those data points. Then we'll calculate a sample standard deviation and sample mean. All right. So let's talk about how we do that. So the sample mean is just essentially the mean, what we've talked about. You add up all the values and divide by how many you have, right? That's the familiar mean that we've know and love. And then we have the sampled standard deviation there also. There's the formula. We typically you don't need to memorize that or anything like that. Basically every software package that you'd use, Excel, MATLAB, LabVIEW, all of them have that formula built into it, and you typically just use the tool to calculate the sample standard deviation. All right, once we have those two numbers, we can calculate the confidence interval using student's T table. All right, so with this, what we're going to do is we'll take the sample mean, and the confidence interval is defined as the sample mean plus or minus the sample standard deviation times the t-value. And the t-value is what comes from the student t-table. All right, so the way that this works is we have to know the degrees of freedom of our data set. And the degrees of freedom are just however many samples we have, data points we have in our sample, minus 1. So on this chart here, we can see our degrees of freedom over on the far left side there. And we have, in this particular small student t-table, 5, 10, 15, 20, 30, and 50 degrees of freedom. So if we had a 5 degrees of freedom data set, that would just mean that there are 6 data points in that data set, right? If we have 10 degrees of freedom, it means we have 11 data points, right? So we just find the appropriate row in student's t-table for our data set, and then we need to pick the t-value out of one of these columns here. And the columns represent the confidence interval, or level of confidence that we have in the data. So the T50 means that we're 50% likely to find the next data point within the range that we set based off of that t-value, whereas the T95 value will give you the confidence interval where you're 95% likely to find the next data point in there. So you just pick the correct value depending on whatever level of confidence you want. T95 is probably the most common for most applications. All right, so this can get a little confusing, so I think the best way to go about this is just kind of do an example of what this looks like. I'm posting these slides in the description below the video here and also up on Canvas, so you can download this and refer back to them also. All right, so what we do here is we've got a data set, and we'll calculate the mean and the standard deviation, sample mean and sample standard deviation for our data set. And we'll get 2 values for that, right? Then we need to know how many data points do we have, and our data points are over in this chart on the right here. And for this one, we have 20 different data points, which means that we have 19 degrees of freedom, right? And to then go and get a 95% confidence interval, what we do is we go to the 19 degrees of freedom row, and we go over to the column for the T95 value, and we can pull that off of student's t-table and plug that into our formula for the confidence interval. So we just take the sample mean plus or minus the t-value times the sample standard deviation, and we've defined our confidence interval, and that's all there is to it. All right? So that is how you perform that calculation. All right. There are some limitations to student's t. So the key thing is the trials that you use to calculate the confidence interval must be independent, right? What I mean by that is you can't have a series of trials where the outcome of one trial can somehow influence the outcome of the next trial that you do. Right, so an example of this would be like if you took a thermometer and you stuck it in a glass of 0-degree ice water to calibrate the thermometer, and we were going to take a bunch of measurements to determine our confidence interval at 0 degrees C. Right, if you just stick the thermometer in the ice water and you quickly write down 10 measurements of whatever the dial says over the course of a couple of seconds, that's not going to be 10 independent trials, right? Because you didn't allow the system to change. You didn't give it enough time or enough opportunities for the uncertainty that would be realistic when you're actually using the thermometer to come into the measurement here. So that was going to lead to an artificially small uncertainty. Your confidence interval will be too tight, and then you're likely to find values outside of that confidence interval because your samples were not independent. All right, so the way you would do this properly is you would take your thermometer, put it in the water, let it equilibrate, and take one measurement. Then take the thermometer back out, let it come up back to room temperature, then put it back in, take another measurement, take it back out, let it equilibrate again, put it back in, and so on until you get enough data points. It is kind of time consuming because you're waiting for the instrument to come to equilibrium every time you have to take an independent trial, but that is the proper way to do it, where you allow for all the variation that would be realistic when you're actually using your instrument. All right. So one of the things to keep in mind here is with LabVIEW, it is very easy to take trials that are not independent. Like we can take tens of thousands of samples per second with the DAC hardware that we have here in the lab. So what you want to make sure is that you really are putting thought in how would I actually use this instrument out in the real world. Am I allowing the instrument to vary from trial to trial? So if you're calibrating your scale and you need to take repeated measurements of your zero to come up with the resolution of your scale, which we'll talk about in another video, what you'll want to do is put a mass on the scale, take a measurement, take the mass off, take a zero measurement, put a different mass on, take a measurement, take the mass off, take another zero measurement, so that you're allowing your scale to vary and have multiple independent trials. It's a very key thing to do when you're using this technique to determine a confidence interval for your instrument. All right, I've included this as a reference. Download the slides here. This is student's t-table with more degrees of freedom lines on it. And there's a couple of notes. We've given you your confidence interval formula, sample standard deviation. It just references of what those variables mean. And then a couple of notes on syntax. So the student's t-table is not specific to any one problem. There's only one, really there's two types of student's t-table, but it's a universal chart that you can go out and find. So the two versions you'll find are the two tails and the one tails student t-table. The two tails one is the one that we use for calculating the confidence interval, whereas the one tail one gets used a lot in sort of like biomedical research when you're hypothesis testing of can you say that a treatment had a significantly different outcome than like a control group. That's kind of what the one tail table is for. But those tables are universal. You can find them from any source, and they should have the exact same numbers on them, so you don't have to worry about finding like an engineering-specific student t-table. There's no such thing as that. There's just the t-table. All right? And this is, again, posted in the slides, so you can download it and see it in bigger size, so it would be easier to read. All right. So let's sum up what we can talk about with student's t-table, right? So it's going to define a confidence interval based off of a limited number of data points. The confidence interval is a range of values where your next measurement is likely to fall. How likely depends on which t-value you use to calculate your confidence interval. If you use t50, it's 50% likely to be in that range. If you use a 95, it's 95%, 99, be 99% likely, so on. All right. The downside of this technique is that we have to have data, right? So we have to collect data. We need to collect multiple data points to be able to use this technique. The minimum number of degrees of freedom that you can have to use the student t-table is 1, which would mean that you'd need 2 data points, at least 2 data points, and it really works better if you can get at least 4 or 5 data points. But for some applications that may not be practical to run your experiment that many times, or what if you want to estimate what the uncertainty of an instrument is going to be before you collect any data, right? In that case, you're going to need a different technique. So we'll talk about our second technique here, which will be propagation of uncertainties. What if we have some fundamental values that all have an uncertainty associated with them, and we want to do math on those values, throw them into some sort of mathematical model and come up with a result. What is the uncertainty of the result of that calculation, right? So the simplest sort of combination that we could do here is, what if we just have 2 values with uncertainty and we want to add them together? What's the uncertainty of the resulting value, the sum of those 2 values? So in this case, we have 2 lengths, A and B, and both of them have an uncertainty associated with them. We want to know what's the uncertainty of A plus B. Well, if we were to just add the uncertainties, what we would end up doing is overestimating the uncertainty of the sum, right? So keep in mind that typically these precision errors, they follow a Gaussian distribution, right? So if we just simply add the 2 uncertainties together, what essentially we're saying is that the uncertainties are basically the long tail of the Gaussian distribution there, and we're going to add both of them together. But that's very unlikely to happen, that both of the lengths would be off by the maximum amount of the uncertainty. It's much more likely that your your actual A and B lengths are going to be close to the average value, the top of that bell curve. So we don't want to overestimate our uncertainty. All right. The other thing that can happen is we just straight add uncertainties is that if you had a negative value, you could potentially cancel out uncertainty, which doesn't happen. If you take two uncertain values and you put them together, you end up with a more uncertain value as a result. Right? So your uncertainties will never be able to cancel themselves out. So the solution that we have here is that we add our uncertainties in quadrature, or kind of like the Pythagorean theorem. We take the square root of the sum of the squares of our uncertainties, right? And that provides us a good estimate of what the uncertainty of the result of our calculation is going to be. All right, but obviously as engineers we do a lot more than just addition. So how do we take this concept and apply it to a more general form, so that if we need to do multiplication, division, subtraction, any of those operations, how do we handle the uncertainty in those kinds of formulas? So what we have here is we have a generalized way to talk about this. So if we have a some sort of value that's calculated, what we're going to call R, right? And R is a function of many variables. So we're saying R is f of x1, x2, ... all the way out to xn. So we can have as many variables that go into calculating R as we want. How do we figure out what the uncertainty in R is, right? If each of these individual variables has an uncertainty associated with it. And typically we give those individual uncertainties the variable of a little e. All right, so the generalized formula that we have here is we still have our square root of the sum of the squares, but we weight each term with the partial derivative of R with respect to that variable. Okay, so that's what this formula here is showing. Now, why do we have these partial derivatives? Let's talk about that. So consider a formula where we have different operations happening to different variables in here. So I've just taken the kinetic energy formula, which is kinetic energy is equal to 1/2 mv squared. Now, if you have uncertainty in both mass and velocity, which of those uncertainties is going to be the most important? Now, for most combinations of mass and velocity, it's going to be the velocity uncertainty is going to be more important because it's squared, right? So it's going to grow faster than the uncertainty in the mass. So by taking these partial derivatives, we can weight the uncertainty in this sum to make certain uncertainties more important than others, right? And that is the idea behind the partial derivatives. All right, so let's take a look at an example of this, right? So what we have here is we have a copper wire, and we know that its resistance, electrical resistance, is going to be a function of temperature, and it happens to follow this formula here. So we have sort of an initial temperature, R naught, which is 6 ohms plus or minus 3%. And we have this coefficient that describes how the resistance changes with temperature, called alpha, which has an uncertainty associated with it. And we have a temperature that the wire is at, which it also has an uncertainty associated with it. Okay, so what we're going to do is we're going to apply that error propagation formula to this equation and come up with what is the uncertainty of R, the resistance at, it's in this case 30 degrees Celsius. All right, so here it is broken out all on one slide. Again, this will be posted so you can download the slide and take a look at this closer, follow along the calculations. But let's break it down as to what's happening here. So the first step in any of these calculations is to just calculate the nominal value. And the nominal value is the value of the resistance when we just ignore uncertainty. We just do the calculation as normal, right? So for that, we just plug and chug into our formula. We calculate that the nominal resistance of the wire is going to be 6.24 ohms in this case. That's what's happening up there on the top line of this slide, right? So that's our nominal value. So now we need to calculate what's the error, so the plus or minus after the nominal value. So 6.24 ohms plus or minus how many ohms? Right. So to calculate the uncertainty, the plus or minus value, is the first step is we want to go ahead and take our partial derivatives. of R with respect to each of the variables that have an uncertainty associated with them, which in this case would be R naught, alpha, and T. Okay, so we're going to take a partial of R with respect to R naught, which you can see there, and then we've plugged in the nominal values for alpha and T, which appear in the partial derivative for R naught, so that we get a number for that partial derivative. So we're evaluating the partial derivative at the nominal values. Okay, and we do the same thing for alpha and T, so that we get numbers associated with each of those. And now we have our partial derivatives calculated. All right, next up, we're going to get our errors. And our errors need to be in terms of units. They have to have units associated with them. And you should notice in the error propagation formula, all the units should work out so that your uncertainty is in the same units as whatever value you're calculating. If that doesn't happen, then there's something wrong. There's an error with your units or your partial derivatives somewhere in the calculations. This is a good way to check your work. So to get our errors in terms of the correct units, for R naught, we were given that uncertainty term of a percentage, so we need to convert that into ohms, because that's the units associated with R naught. So in this case, we had our nominal value of our resistance was 6 ohms, and we were told that we had a 0.3% uncertainty, so we're going to multiply 6 times 0.00.3 to get the uncertainty in terms of ohms. Okay? And we'll keep doing that. We have to do that with alpha also, and then the error associated with T was given us in degrees Celsius, so we don't have to do any conversions there. That's already got the correct units on it. All right, from there, we're just plugging into the error propagation formula. So we take the partial derivative with respect to R naught times the uncertainty in R naught, square that, do the same thing with alpha and T, and then take the square root of all those sums, and we get a final uncertainty here, so of 0.0305 ohms. All right, we're almost done at this point. So that is our uncertainty, our plus or minus value, but we need to talk about how we report that value. All right, the last step here is that we need to round that. Okay, so the rule with uncertainty, these absolute uncertainties, which means that it's an uncertainty in terms of units instead of a percentage, is that we always round that to 1 sig fig. All right, and the reason we talk about that is if you are reporting uncertainties, the first significant figure, everything after that is uncertain. So it's completely meaningless to report uncertainties to more than 1 significant figure because you don't know anything about the figures after that first significant figure anyway, so they're by definition not significant figures anymore. Okay, so our 0.0305 ohms, we're going to round up to 0.04 ohms. All right, why are we rounding up? So we never ever want to underestimate our uncertainty. So we always round our uncertainties up. Even though normally we would round that to 0.03 ohms, we're going to round it up to 0.04 ohms just so that we're taking no chances and we're not going to say that our instrument is more precise than it actually is. All right, so here's the summary on propagation of uncertainties. This is handy for design work because you can estimate the uncertainty before building an instrument. If you derive what the experimental calibration curve of your instrument, or sorry, the theoretical calibration curve of your instrument is supposed to be, you can apply this formula to that equation for your theoretical calibration curve, and you can estimate what the uncertainty of your instrument is going to be if you know the uncertainties of different components that go into that measurement are ahead of time. So it can be useful for design work. It can take into account uncertainties of constants used in calculations. So if we have constants programmed into a LabVIEW code that have uncertainties associated with them, LabVIEW's not doing anything to take into account those uncertainties. So if we were to try and do student T method where we just take repeated measurements, those constant values are not having their uncertainty taken into account, and we would underestimate the uncertainty of our overall measurement without taking the uncertainty of the constants explicitly into account by doing propagation of uncertainty. Right. The downside of it is you do have to have a mathematical function describing how your sensor or instrument works or how your measurement works, which may not always be feasible to derive. And sometimes you just have to estimate your uncertainties experimentally. That's the best that you can do. All right. Okay, so to finally wrap up, your student's t-table, you want to use that when you have multiple independent trials that are possible. Propagation of uncertainties, more for design work, or when you can't do multiple trials, you can usually do propagation of uncertainties. And sometimes you can use a hybrid approach. Like sometimes you can use student t to find uncertainty in, say, like a voltage measurement, and then you can use propagation of uncertainty to take that uncertainty that you found with student t and propagate it through whatever math that you're doing in your analysis of that voltage measurement to come up with a final value. That's totally valid to use a hybrid approach that way also. All right. But that is it for me today. We have all of these slides will be posted in the YouTube description and up on Canvas. And we also have an activity which you can do entirely remotely if you choose, where you get to practice a couple of these calculations. So be sure to check that out, turn it in, and get your credit. But good luck, and stop by and ask questions if you have them.